This essay explores an intriguing analogy between large language models, or LLMs, and quasi-crystals, suggesting that LLMs generate text with a form of coherence that doesn't rely on repetition, much like the unique structures found in certain materials. Let's break this down step by step. Large language models are advanced computer systems trained on vast amounts of human text. They use deep learning techniques, particularly the transformer architecture, to predict the next word or token in a sequence based on what came before. A token is basically a building block of text, like a word, part of a word, or a punctuation mark. These models don't follow predefined rules of grammar or meaning. Instead, they generate fluent and contextually appropriate text through statistical patterns learned from their training data. For example, since the release of models like GPT-2 in 2019 and GPT-3 in 2020, LLMs have demonstrated the ability to produce language that's locally coherent and thematically consistent across various topics. This means the text flows naturally and makes sense in the moment, even though it's driven by probability rather than true understanding or intention. The output often appears intentional or thoughtful, but it's really the result of recognizing and replicating patterns at a massive scale. Now, to understand the analogy, we need to look at quasi-crystals. These are a type of solid material that was first discovered in 1982 by scientist Dan Shechtman. At the time, it upended traditional ideas in crystallography because quasi-crystals show long-range order without the periodic repetition that was thought to define crystals. In classical crystals, atoms are arranged in a repeating pattern, like a grid that tiles perfectly across space. But quasi-crystals don't do that. Instead, they have a structured arrangement that's deterministic and orderly, yet aperiodic, meaning it doesn't repeat in a regular cycle. This was a big deal because it challenged the fundamental assumptions about what constitutes order in physical systems. Quasi-crystals can exhibit symmetries, like five-fold rotations, that aren't possible in periodic crystals. Early models of these structures, developed by researchers like Levine and Steinhardt, used things like Penrose tilings to show how complex, non-repeating patterns can emerge from simple local rules. This discovery expanded fields like materials science, leading to new insights into symmetry, entropy, and how materials self-assemble. The essay proposes that the output of LLMs behaves similarly to quasi-crystals. Specifically, the sequences of text generated by LLMs display local coherence, meaning the words and sentences fit together smoothly, without relying on global repetition or a fixed structure. Just as quasi-crystals are neither random nor perfectly periodic, LLM-generated text is structured in a way that's statistically constrained but varies in unpredictable patterns. Each token is chosen based on the context of the previous ones, creating a flow that's internally resonant and organized, yet not repetitive. This perspective shifts how we think about LLMs. Traditionally, we evaluate them based on things like predictive accuracy, how factual they are, or how well they align with human values. But this analogy highlights their ability to produce quasi-structured outputs, text that's coherent through constraint-based organization rather than explicit rules or symbolic intent. In other words, LLMs aren't just imperfect mimics of human intelligence or random generators. They're systems that create emergent patterns, much like quasi-crystals form in nature. To support this idea, the essay draws on philosophy of science and language. It references concepts like structural realism, which emphasizes the importance of underlying structures over direct representations of reality, and inferentialist views of meaning, which suggest that meaning arises from how elements relate to each other rather than inherent properties. For instance, in scientific representation, models don't have to perfectly mirror the world. They just need to capture key structural relationships. Applying this to LLMs, the coherence in their output emerges from the way tokens connect and propagate constraints, even if the overall meaning is emergent or partial. The essay also introduces the notion of structural evaluation as a new way to assess LLMs. Instead of focusing solely on semantics, like whether the text is accurate or truthful, this approach examines how well the generated text maintains constraint, variation, and order across different spans. For example, does the text sustain a logical flow without falling into repetitive loops? Does it introduce variation while keeping things coherent? This method complements existing evaluation techniques by prioritizing formal patterns over content-based metrics. By framing LLMs through this quasi-crystal analogy, the essay suggests we're seeing a new mode of coherence in generative language. One that's based on statistical and local rules rather than traditional notions of order. This isn't to say the analogy is perfect. Quasi-crystals are physical materials with atomic arrangements, while LLMs produce abstract sequences of text. Still, it provides a useful conceptual tool for understanding how coherence can arise in systems where meaning isn't straightforward or fully accessible. The authors point out that other systems, like cellular automata, also generate complex behaviors from simple local rules, but quasi-crystals stand out for their specific blend of order and aperiodicity. This comparison helps reframe the discussion around LLMs, encouraging us to appreciate their structural properties as a key feature, rather than viewing them solely through the lens of semantics or performance. In essence, just as the discovery of quasi-crystals redefined order in physical sciences, this analogy invites us to rethink coherence in artificial language generation. It opens up possibilities for exploring how LLMs create resonant patterns that feel meaningful, even in the absence of deeper intention or repetition. This structural view could lead to better ways of designing, evaluating, and interpreting these models in the future.